Welcome back. We're in section 314. We're going to be talking about exponential decay. And exponential decay is when we decrease from left to right, unlike growth where we increase from left to right. So that's what we're going to be talking about. We're going to skip the Penny Lab. That's what we would do if we were in class together, but unfortunately we're not. So let's go and talk about half-life. And half-life is something you'll hear about in science classes and even in history classes when you're talking about carbon dating. And that's what this first problem is about. They can use carbon to discover how old an object is because of the half-life, knowing that the rate of decay for a certain carbon-14. So they're saying that the half-life is 5,730 years. So what half-life means is it's losing half of its amount of carbon over that time period. So looking at it, they're saying if we start off with 100 grams, how much would you expect after one half-life? So what we have here is our initial 100 times, now our multiplier is 1/2. We have half of our value. So in one half-life, we'd have 50 grams. Now, in two half-lives, you'd have 100 times 1/2 squared for that two half-lives. So 100 times 1/2 squared would be 25 grams. If we did three half-lives, 100 times 1/2 to the third, we'd have about 12.5 grams. And you can see we're just dividing that by 2 each time. If we had four half-lives, 100 times 1/2 to the fourth, we'd be at 6.25. So now if we think about graphing this, I'm going to draw like a really quick graph. About 100, and then a 50, and then 25, and then 12.5, 6.5. No matter what, we would never reach 0. We're going to get very close to it, but we're never going to quite reach it. So what's going to happen is our graph, we can connect it because we can have those years in between, but we never get to y equals 0. We have that horizontal asymptote. No matter how many times you cut it in half, you're going to get very, very small, but never quite to 0. So for our function, y equals a, our initial, 100, times our multiplier, 1/2 to the x. That's our exponential decay model. Notice that the number in parentheses is less than 1. That's what creates it to be, exponential. So now let's look at the exponential decay model. So for our exponential decay model, y equals a times 1 minus r to the t, where the rate is written as a decimal, and t is the time in years. Once again, it doesn't really matter if you use x or not, and a is your initial. But notice for decay, we're subtracting. So a new smartphone, to tell you're decaying, you see that word decrease or depreciation. We'll be looking at those. So we're going to write a model. Now it costs $1,200 initially, so it's going to be decay. So they want us to use v equals a times 1 minus r to the t. A is 1,200 times 1 minus. Now 60% is 0.6 to the t. So v equals 1,200 times 0.4 to the t. There's our decay model. Now we can use that model for 3 years. So V equals 1,200 times 0.4 to the third. You're going to get about $76.80 after 3 years for that $1,200 smartphone. And if you've ever bought smartphones and tried to trade them back in, you can see that those are pretty realistic numbers. So a new car, also something that depreciates pretty quickly. So our cost, Y, equals A times 1 minus R to the T. Started out at $30,000. 1 minus 0.25 to the T. Y equals 30,000 times 0.75 to the T. That's our decay model. Now we can use that for any number of years. Now for 4 years, 30,000 times 0.75 to the fourth. So about $9,492.20 is what that value would be after 4 years. Laptops, it's decreasing, it's depreciating, losing value. So they want us to use V for the value. So V equals A times 1 minus R to the T. 1,000 times 1 minus 30% is 0.3 to the T. So our model, 1,000 times 0.7 to the T. So when we're looking at 4 years, 1,000 times 0.7 to the fourth. So that laptop would be worth about $240.10 in 4 years. So this is exponential decay. All right, so decay, unlike growth, we're subtracting the rate instead of adding. That number in parentheses should be less than 1. Between 0 and 1, excuse me. Okay, thank you, and I'll see you in the next video.